So, continuing with our solutions to the Fick's second law, let us consider the following case. Consider two semi-infinite bars joined together to form what is called a diffusion couple. So, the situation is like this. I have two bars which are joined together, two long bars. For all practical purposes, they could be considered as infinite in both directions, and of let us say some alloy AB. So, B is a solute. So, to begin with, this bar has a concentration of B atoms given by C1, and the bar on the right hand side has a concentration of B atoms as C2. So, which means that on the left hand side I have a concentration C1, and on the right hand side I have a concentration C2. So, this is C1, this is C2, and this is the concentration profile at T equal to 0. So, this entire diffusion couple is kept at an elevated temperature T, so that B atoms could diffuse from the left to right. C1, the concentration on the left hand side of B atoms being higher than the concentration of B atoms on the right hand side. So, after some time T at this temperature, the concentration profile of B atoms would start to look something like this. So, this is at some time T. So, this kind, if I want to know how this profile is going to change as a function of time as well as of course as a function of distance, I would need a solution to the Fick's second law, del C by del T is equal to d del square C by del x square. So, without going into any derivation to this solution, the solution to this is given by how the concentration changes as a function of x, the distance, and time t. Cxt is given by some constant a plus a constant b times a function called ERF, or the error function, x upon 2 square root of dt. Now, what is this function f, or the error function? Just a quick look at this function. Error function of z is equal to 2 upon square root of pi integral 0 to z e to power minus eta square d eta. Now, this integral does not have an analytical solution, that is why the solution is written in the form of a error function. If I plot this function e to power minus eta square versus eta here, then this is the way, this is the shape of the function. So, if I look at what is the error function z, so I locate z on this axis, then the error function of z is nothing but the area under this curve in this region. So, if I look at it, what is error value of error function at some specific values of z? For example, what is the value of the error function at z is equal to 0? So, error function of 0. Well, this integral is going to be integrated from 0 to 0, hence this integral will become 0. The area under the curve is 0, and hence the error function at z is equal to 0 is simply 0. Another special value of the error function at plus infinity. So, we are looking at area over the entire curve from 0 to infinity. Then this value is simply 1. Error function at minus infinity, you are looking on this side now, it is simply minus 1. And very clearly error function of plus z would be equal to minus error function of minus z. So, these are some specific values that you can take a note of for the error function. Values of error function at other z values, for that we will make use of a table of error function little later. So, now coming back to this solution, Cxt is equal to a plus b error function of x upon 2 square root dt. We need to find the constants a and b. So, let us apply the boundary conditions. So, let us look at this problem now. What is the concentration far away from the interface on either side of the interface, but far away? Far away on the left, the concentration will be C1, far away on the right from of the interface, the concentration will remain as C2. So, therefore, the boundary conditions I can write is at C on the left hand side at x going to minus infinity at any time t, the concentration is fixed at C1. Similarly, on the right hand side C plus infinity at any time t, so far away on the right hand side the concentration is fixed at C2. We substitute these boundary conditions in the solution here, which means on the left hand side putting x is equal to minus infinity, C1 is equal to a, and if I look at, I put x for minus infinity, this will become error function of minus infinity, and error function of minus infinity is minus 1, hence this is equal to a minus b. Similarly, the second boundary condition C infinity comma t is C2, which is again a, but this time I put in x is equal to plus infinity, so this will be error function of plus infinity, and error function of plus infinity is plus 1, hence C2 is equal to a plus b. From here I will get a equals C1 plus C2 divided by 2, and b equals C2 minus C1 divided by 2. Hence, now we have it that the profile, concentration profile of the B atoms in this diffusion couple is given by C1 plus C2 divided by 2 plus C2 minus C1 divided by 2 error function of x upon 2 square root of dt. So, this gives me the solution of how the concentration is going to change in a diffusion couple. So, if I know what is the diffusion coefficient at the temperature at which we are studying this, then from here I can predict how the concentration of the solute B atoms is going to change at different locations x and at different times. Where a similar solution or the same solution applies is the following. Consider a constant surface concentration of solute atoms. So, surface concentration of B atoms at one end of a semi-infinite bar. So, the situation is I have a semi-infinite bar where I am keeping the concentration. So, this is, let us say, a bar of, let us say, A atoms, and I am keeping, or for that matter not just A, it is an alloy of AB with some concentration C0 to begin with, of C0 concentration of B atoms. And if I look at this, so this is how, so this is C0, that inside the bar there is a C0 concentration of B. The surface is kept at a concentration of B atoms as C sub S, the surface concentration. This can be done, for example, in the case of carbon, one can have a carburizing gas that this surface is exposed to in such a way that the concentration on the surface of carbon atoms is fixed at Cs. So, initially the concentration profile of B atom is simply this. After some time t, the profile would become something like this. So, this is at t equal to 0 and this is at some time t greater than 0. Again, we are talking about some temperature T at which we are doing this experiment. And the concentration of the surface is kept fixed at Cs all throughout. In this situation also, this particular solution applies. And all we need to do is find the constants A and B for the given boundary conditions of this particular problem. Now, what are the boundary conditions here? Well, this is x is equal to 0. So, at x is equal to 0 for any time t, the concentration is kept fixed to Cs, as I have already mentioned. So, this is one condition. This is a semi-infinite bar. So, far away from the surface, the concentration of B inside this bar is simply C0. So, the second boundary condition is C at plus infinity at any time t is equal to C0. Apply this boundary conditions to the solution. So, I will get C0t equals Cs is equal to at x is equal to 0. So, if I look at this at x is equal to 0, I will get an A plus error function and x is 0. So, error function of 0 we already know is 0, hence I get Cs is equal to A. Apply the second boundary condition, C infinity t is equal to C0 is equal to, coming back to this solution, I will get A plus B error function of infinity. Error function of infinity we know is 1 and hence C0 is equal to A plus B. From here I already have now A is equal to Cs and B is equal to C0 minus A or C0 minus Cs, and hence from these boundary conditions I get the solution Cxt of the concentration profile as a function of distance and time as Cs plus C0 minus Cs error function x upon 2 square root dt. So, this is the solution in this case. Now, this we will take up in the next lecture, not in this lecture. We will take up a problem where we can actually apply this solution, and what is the this particular relationship has a great practical application, as we will see in the next lecture. Now, we have looked at the solutions, we have solved the solutions of the Fick's second law. The coefficient d has kept coming up in all the solutions, and in fact you will notice in all the solutions the term square root dt keeps coming up. Right from the first lecture on diffusion, but we have not really talked much about the coefficient d, and therefore in this subsequent part of this lecture I will now talk about the diffusion coefficient d. What is it made up of? We have some idea of the diffusion coefficient d right in the first couple of lectures, and we will expand from that. So, I am now going to examine this diffusion coefficient and what does it depend on. You would recall from the first couple of lectures on diffusion that the diffusion coefficient d we found out was proportional to the jump frequency of atoms times lambda square, where lambda is the jump distance. So, lambda would typically be an interatomic distance, and this jump frequency, and in fact in one specific case when we had taken diffusion in a simple cubic crystal, we had found d to be equal to 1 upon 6 nu prime lambda square. So, there was this factor of 1 upon 6, in some other situation this factor of 1 upon 6 could change. So, in general the diffusion coefficient is going to be proportional to nu prime upon lambda square, no, nu prime times lambda square. So, lambda I will just put as inter-atomic distance for the jump, and nu prime is the jump frequency per second. So, this is clear. Now, let us explore nu prime, the jump frequency. What is it going to depend on? Well, first of all, it will also depend on whether we have, what is the mechanism of this diffusion. So, whether we have interstitial diffusion or we have substitutional diffusion. And it would also be dependent on the lattice vibration frequency. Nu, which is can be generally taken as 10 to power 13 per second. So, let us examine the two cases of interstitial and substitutional diffusion and how is the jump frequency going to depend on these two mechanisms. So, let us consider interstitial diffusion. So, imagine that this is an interstitial atom. So, this is atom A and out here is atom B. Now, if it has to jump from one interstitial site to another interstitial site out here, it has to squeeze between these two atoms. So, one can imagine a situation that in order for this to jump, there would be a position where these two atoms would be displaced and this atom would have come to this position and the next position would be that. So, it jumps from here to an intermediate position and then finally to the position in the neighboring interstitial site. So, I have let us say position 1, position 2 and position 3. And if I were to look at the energies associated with each of these positions, so the situation would be something like this. So, this is at position 1, this is at position 2 and this is at position 3. So, position 1 and position 3 are equilibrium positions, low energy positions, while at position 2 the crystal is taken to a high energy state. Therefore, for this jump to be successful, the interstitial atom has to have sufficient energy for it to jump over this energy hill. And what is this energy hill? We will call this as delta Gm, the migration free energy. So, we will call delta Gm to be equal to a migration free energy. Something similar exists. So, this is for the case of interstitial. Let me write it here. What about substitutional? A similar situation also exists for substitutional diffusion. Let us say this is my solute atom. So, this is A atom, this is B atom. Now, if it has to jump to a neighboring site, this neighboring site has to be vacant. So, let us say that this is a vacant site. So, in order for this to jump again, it has to squeeze between the other neighboring atoms, and as a result this jump would also be associated with a migration free energy or an energy hill of this kind. And so, therefore, in both interstitial as well as substitutional diffusion, there is a migration energy involved for an atom to jump from one location to a neighboring location. So, hence there is a probability of a successful jump. So, what is that probability? So, probability of a jump would be equal to exponential minus delta Gm divided by kT, just like we had seen in the case of nucleation also, or jump of atoms across the interface, etc. It is a similar kind of expression that this is going to be related to the probability of a jump, and hence what is the frequency of jumps then? Well, atoms are vibrating with a frequency of nu, and hence nu prime, the jump frequency, is equal to nu times exponential minus delta Gm upon kT. Now, this is the situation for the case of interstitial diffusion. So, we have seen that in the case of interstitial diffusion, jump frequency nu prime is given by nu, the lattice vibration frequency, multiplied by exponential minus delta Gm upon kT, where delta Gm is the migration free energy for the jump. Now, we can write delta Gm in terms of enthalpy and entropy as delta Hm, the enthalpy for migration, minus the temperature at which the jump is taking place, times the migration entropy delta Sm. So, substituting this, the jump frequency for interstitial diffusion is given by nu exponential, substituting for delta Gm, I will get exponential delta Sm upon k times exponential minus delta Hm divided by kT. If we can assume delta Sm to be independent of temperature, then I have the pre-exponential term nu exponential delta Sm upon k to be independent of temperature, while the exponential term is dependent on temperature. Now, consider the substitutional diffusion case where the vacancy mechanism is active . So, in the case of substitutional diffusion, also one can write nu prime to be equal to nu exponential minus delta Gm upon kT. These terms would still be there. However, there would be one more term that would have to be added to this expression, because for a jump to be successful, the neighboring site to which the jump is taking place has to be vacant. So, if I have an solute atom jumping here, which means this site must be vacant. What is the chance that this site will be vacant? So, therefore, we have to multiply this expression by the probability that the site is vacant. And what is the probability for a site to be vacant? So, probability of a vacant site has to be given by what is the enthalpy of formation of a vacancy, and this is given by exponential minus the enthalpy for formation of vacancy, which I am calling it as delta H vacancy, divided by kT. This probability will have to be multiplied here, Now this particular probability comes from a simple exercise in a very basic material science course. So I will not go into the details of how this expression is coming. So very clearly the substitutional diffusion is going to be more difficult, or the jump frequency is going to be less than in the case of interstitial diffusion, because you have an added term which is the probability of a site being vacant. Now let us substitute for delta Gm in terms of delta Hm and delta Sm as we have done here. For substitutional diffusion, the jump frequency would become nu exponential delta Sm upon K, the temperature independent terms, as in the case of interstitial diffusion, times exponential minus delta Hm, and there will be an additional term, an additional enthalpy term, vacancy enthalpy for creation of a vacancy. So delta Hm plus delta H vac divided by Kt. So you can compare the relationship for jump frequency for interstitial diffusion, and in the case of substitutional diffusion, the additional difference is simply the enthalpy for creation of vacancy. Now in general, I can express for interstitial diffusion nu exponential delta Sm upon K times exponential minus Q. Instead of writing delta Hm, I am writing Q, and I am writing this Q in terms of energy per mole, and hence instead of writing the Boltzmann constant K, I will replace it by R. I will write it in this fashion, where Q is called as the activation energy for diffusion. In terms of the typical units can be joules per mole inverse, and R is the gas constant instead of writing the Boltzmann constant. Similar thing I can do for substitutional diffusion, and I can get an identical relationship: vibration frequency nu times exponential delta Sm upon K, the temperature independent part, times exponential minus Q divided by RT, where here Q consists of delta Hm plus delta vacancy, here Q simply consists of delta Hm. But we can write both of the equations in a very similar way, except that the activation energy would be different for substitutional diffusion and interstitial diffusion. So going from here, jump frequency, whether it is interstitial or substitutional diffusion, is, I am simply rewrite that as nu exponential delta Sm by K exponential minus Q by RT, and right in the big earlier part of the lecture I had written diffusion coefficient is proportional to nu prime lambda square, hence we can write the following relationship for the diffusion coefficient. I can lump, there will be some constant of proportionality here, which is going to be a function of the geometric factors like what kind of a crystal structure, in what direction you are considering diffusion, etc. And in addition to that, jump distance and nu prime, which is coming from here. So D could be written as all the temperature independent terms can be lumped into parameter D0, e to power minus q by RT. So, this represents the final expression for diffusion coefficient as a function of temperature. Here D0 is also termed as the frequency factor. And Q is called the activation energy for diffusion. And one final thing before I terminate this discussion in this lecture, if I collect different values of diffusion coefficient from diffusion experiments as a function of temperature, then I can find out from that data Q and D0, and then I will be in a position to determine D for different values of temperature. And how can I find Q and D0? So, I will get diffusion coefficient values D for different temperatures, and suppose I take logs of this equation, then log D is equal to log D0 minus Q by R times 1 upon T, and if I plot log D versus 1 upon T and I put in the data points I get for different temperatures, what is the diffusion coefficient, they should fall on a straight line. So, I put a best fit line through this, and from the slope and the intercept I can get the value for activation energy and D0, and after that I can get D values for other temperatures. So, just to give you an idea of the order of magnitude estimates for the diffusion coefficient, let us consider some data that is available. So, order of magnitude estimates. Consider the system, what is the value of D0 for it, what is the value of Q for it. D0 is in units of meter square per second inverse, Q I am going to put it as kilojoules per mole. So, consider diffusion of aluminum in aluminum, that means we are considering self diffusion. D0 is 2 into 10 to power minus 4 and Q is 143.4. Copper and copper, D0 is 2 into 10 to power minus 5, Q is 196.5. So, these are a couple of examples of self diffusion. Consider carbon in gamma iron, that is we are saying carbon in austenite, a face centered cubic form. What is the diffusion? Diffusion of carbon in the body centered cubic form of iron will be different from the diffusion of carbon in austenite form of iron. In this case, I get D0 as 2.3 into 10 to power minus 5 and Q to be 148 kilojoules per mole. Zinc in copper, now this is the case of interstitial diffusion. And here this is the case of substitutional diffusion. So, zinc in copper, D0 is 3.4 into 10 to power minus 5 and Q is 190.7 kilojoules per mole. If we take just one case, let us consider this case and let us find out what is d, the diffusion coefficient at T equal to 950 degrees centigrade? Well, d is equal to d0 e to power minus q by RT. So, d0 is 2.3 into 10 to power minus 5 times exponential minus 148 is the value of q, but it is in kilojoules. So, I have to multiply it by 1000 to convert to joules, divided by the gas constant, which I am going to take it as 8.31 joules per Kelvin, times the temperature in Kelvin. So, I have a temperature of 950 degrees centigrade, add to this 273 to give me 1223 Kelvin as the temperature. I calculate this and I get a diffusion coefficient value at 950 degrees centigrade for carbon and gamma iron as 1.09 into 10 to power minus 11 meter square second inverse. What would happen if I increase the temperature? Well, it is very clear from this equation that the diffusion coefficient value will go up. So, you will have faster diffusion. As the temperature is reduced, the diffusion coefficient value goes down and you will have slower diffusion. So, this brings us to the close of this lecture, and in the next lecture would be the concluding lecture of this course, where we will conclude what we have done and what kind of applications we can apply the fundamentals that we have done here. Thank you.